So we're going to talk about variables and memory management generally. We'll talk about memory structure, what the life cycle of a variable is in a C program, variable scopes, which you may not have heard of before if you've spent all of your programming time in Python. This includes global variables versus macros and preprocessing. And then we'll spend a good amount of time talking about variable types, because types are something you may not have encountered before if you haven't used a strongly typed programming language before. So, in C, in fact, in all programming languages, variables are positions in memory which act as storage points. Right? These variables, when you declare a variable, they have to exist in memory somewhere. The variables are positions in memory which act as storage points. However, we typically work with the names of variables rather than the addresses, because it's a lot easier to remember the value of A, or the variable name A, than it is to remember a long integer value, which is where the variable A is stored. In C, a variable declaration looks like this. You'll have a type and then a name, and frequently you'll have that set equal to some value. And that whole statement is ended with a semicolon. If you haven't used C before, the semicolon is important. If you try to compile things and you don't have it, it won't work. These are some simple example declarations and initializations in C. So we have an int A set equal to 1. We have a double C set equal to 1.0. And we have a size type D set equal to 1. You may have come across ints before. You may have come across doubles before. If you've never used C, you probably haven't used a size type before. So every variable here has a type, int double size t. It has a name, ACD. I don't know why I skipped B. And eventually it has a value, because if it doesn't have a value, then it's not used. So this begs the question, what if we want to declare a variable without assigning a value? There are plenty of reasons why you might want to do that. In this simple example, we have int main, because of course every C program has a main. We have int x set equal to 4, then we declare int y, but we don't assign it a value. And then we assign an integer pointer z to the location of x, or the address of x. We can try to reason about what the memory for this program looks like, in like an abstract sense of a mental model of the memory. So here we just have a table. We have addresses on the left, we have values in the center, and then the code, roughly, that corresponds to that on the right. So address, I'll just say 1,000, we have a value of 4, int x equals 4. That much is clear. At address 1004, we have a value which is 0 here, which is int y. This means that y is initialized to a 0 value initially. And then at 1008, we have a value which is actually just the location of x, right? So it's saying that our integer pointer for z looks at the location of x. So x is an integer with a value of 4. Variable y is an integer with unassigned value. In C, the value is usually initialized to garbage data or 0, but it is formally undefined. And I'll spend a little bit of time tomorrow talking about some of the subtleties of C and undefined behavior. And the integer pointer named z is set to the address of x, i.e. the ampersand followed by x. Now, when we reason about our program, when we write our program and we make allocations in that program, we are writing to memory, but we think about this in terms of two different types of memory, the stack and the heap. Understanding where our variables are allocated to will help us to write fast, hopefully correct programs. For the stack, this is located, it's fixed size and it's located at the beginning of the program in memory. The allocations here are typically fast. I say typically in the sense that you are typically allocating very small things. So when you write int x equals 4, you are making an allocation to memory. But because it's a single integer, if it's on the stack, that's quite fast. This is almost always scope explicit. So you have to follow function call semantics. We'll talk a bit about scoping in a bit, and you'll talk about function call semantics later on in the session. The nice thing about the stack is that it's typically compiler and OS managed. So it's not up to you, the programmer, to remind the program that you allocated a single integer at the very beginning. It knows, and it's going to take care of it. On the other hand, being restricted to only allocating single integers is quite limiting, not super useful. This is where the heap comes in. This is a flexible size bit of memory. It changes during the runtime. It has slower allocations, typically. This is typical, again, because the allocations are typically larger. It's managed exclusively with pointers. So you are giving your program locations in memory to address. And the allocation and deallocation are programmer responsibilities. So the compiler and the operating system won't handle this for you in, except very limited cases where it can prove that things don't matter. These two regions of memory are usually modeled as growing towards each other, right? Because one's at the beginning of the program. The heap is typically thought of as at the end of the program because it changes size. And if you use enough of both, they might collide and you'll get some sort of undefined behavior. In practice, that's not really true. If you've been using computers for the past couple decades, you have perhaps learned that the model you have of how a computer works is no longer valid. Your program is not running raw on the hardware, it's running through dozens of layers of abstraction, through the OS, through firmware, through all sorts of things. This sort of memory collision is not so much an issue anymore. This is both for security and practical reasons, and also because compilers have gotten a lot better. Now, I told you that variables are locations in memory, but we work with variable names rather than their locations, because their locations are just integers. There's quite a few of them. Variable identifiers, the names, are much easier to work with, but there are restrictions. In C, the names are a sequence of letters and numbers, provided the first character is a letter. And for the purpose of variable naming, the underscore is treated as a letter in C. The variable names are also case sensitive, so these examples are all valid. So you have a float, lowercase electron underscore mass set equal to 1, a float electron underscore mass all caps set equal to 0, an integer C14, and a double U equals 0.5 times 10 to the minus 4. Those four are all valid declarations of variables. Likewise, variables cannot overwrite essential keywords in C. So you can't have a variable named if, you can't have a variable named for, so you can't write int if equals 0. You can perhaps tell there's a hint here because of the syntax highlighting. The int is in red, the if is in green, whereas all these other variables are in black. That's because if is a reserved keyword in C and in fact in most programming languages. So here we have a little quiz, which will be hard to do with only myself and Eva in the room. Which of the following are not valid C variable names? So they're int ddx2 d2 dx2, d2 dx2, 2d ddx3, double x, underscore double. The syntax highlighting does give a hint. Yep, so 6 is not a valid variable name, you can tell, because you're trying to declare the reserved word double as an int. Double is reserved, you can't use it as a variable name. There's one more. Number 4, yes. So you can't start it with a number. It has to start with a letter or an underscore. So 4 and 6 are not valid variable names. Are these good variable names? The ones that are valid, at least? Yeah, I would say these are not good variable names. I have used all the valid ones in programs that I've written. Sometimes you just need to declare something and you don't much care what it's named. But no, these are typically not good variable names. You usually want something more descriptive. And if you like, we can chat about more systematic ways of declaring variable names tomorrow. Now let's talk a bit about the variable lifecycle. This is a very short example program. It is valid, it compiles, it runs even. You always start with a declaration, because if you don't declare any variables, your program doesn't do anything. So here we have int a, and then b equals 1. Then we set a equal to 2 times b, and then we print a. So we start with declaration, then we assign. So here we're declaring a, we're declaring and assigning b, and then we assign a. Then we retrieve. For example, when we assign to a, we are retrieving the value of b, and in the printf, we are retrieving the value of a. And then you free. You deallocate. Now, because this is stack allocation, we don't have to worry about it. The compiler will insert the necessary code to deallocate the program. Deallocate the variables in this program. In fact, even if it doesn't, this is such a short program that it may not matter. The question I have for you is, where in this program does the deallocation of A occur? What about the deallocation of B? Yes, so variable A is certainly deallocated once you leave the program, because you've used it in the final line. In principle, B could be deallocated earlier. It could be deallocated before that print statement. In practice, this is rarely an issue. The code that the compiler inserts to deallocate stack allocations is done in a location where the compiler can prove that it won't affect the correctness of the program by doing that. But it's good to keep in mind. This brings us to variable scopes. Variables are always defined in a particular scope. This is the program block where the variable is declared, defined, and used. In C, all identifiers are statically scoped. We'll get to what that means in a second. So variable bindings are determined by the program text. That is, the binding of the variable is determined by the actual text in the code. The compiler searches the current block, then it searches the global scope, and then it searches smaller scopes in order to figure out where that variable is defined. And a block, if you don't know, is delimited by curly braces. So when you define a function and you've written some code inside of those curly braces, that is a block. It is the function's scope, and if you bind variables in that scope, then those variables are accessible in that scope. Unless you use something outside of it, then the compiler has to search for where that is. Typically, it's good practice to restrict yourself to things in the current block and have very few global variables, and to not rely on anything being in smaller scopes. Scopes are really significant for functions, which we'll discuss later in this course. So let's talk about scopes a bit. So that's standard I/O, which maybe you learned a bit about yesterday. That's just for printing, because all of these programs are compilable and runnable. It helps if it actually does something. We have our int main, and then we have int a equals 1, and then we printf the value of a. And then we create a new scope, and we say int a equals 2, and we printf a. And then another new scope, int a equals 3, and we printf a. Then we go back to scope 1, we print a again, and back to our main function scope, and print a again. What is the output? This first line is hopefully clear. Nothing confusing yet. There's a single scope. A equals 1, and then we print out the value of a. So the first line should be a equals 1. What about here? A equals 2, and then a equals 3. And then we go back to scope 1, where a equals 2, and then we go back to the main scope, where a equals 1. So it should be 1, 2, 3, 2, 1. Now this is a very simple example. These scopes are perfectly nested. You can imagine we could make something much more complicated. Something to keep in mind is because the variable a is allocated anew within each scope, it does not modify the outer scope. The assignments in the outer scopes are still valid. That's why when we go deeper into the scope hierarchy and then back out, things reverse perfectly. This is the same program, except we're not reallocating a. We are just reusing the existing variable name. So a equals 1 is the same, then a is equal to 2a, a is equal to 3a, and then we back out the scopes again. So the first line is 1, and then the second line is 2, and the third line is 6, and what is the fourth? 1, 2, 6, 6, 6. So in scopes 1 and 2, a is modified, it's not redeclared, so the initial declaration is reused. You can imagine if these were complicated functions rather than just assignments and printing, this could be quite hard to follow. Here we have a third example. Int a equals 1, then int b is equal to 2a, int c is equal to 3b, and then we print the values of b and a again. So here we end up with a equals 1, b equals 2, c equals 6, and then b equals 2 and a equals 1. In scope 1/2, b/c is assigned during the declaration of a/b in a higher scope. I don't blame you if this is not immediately clear to you, but I encourage you to just copy this program and compile and run it and see if you can understand what's actually happening behind the scenes. Now we can talk about global variables. So these are variables in global scope. They're defined outside the scope of any function, including the main function. You can imagine for C, this makes them quite important. And their importance really stems from the fact that any function in your program can access that value. This also means that any function can modify that value, in principle. You can imagine that this leads to a lot of very subtle and annoying bugs. To avoid accidental modifications, it's useful and performant, so it's a good idea to do, just generally, is to make your global variables read-only using the keyword const. That means constant. It means that the value and the type cannot be modified. If your function does need to modify the variable, typically you should move the definition of that variable to your main function so that it's within the main scope and it can be modified by functions called from main. Another technique people sometimes do is they define it as a const globally, and then they make a local copy of that when they need to modify it inside a function. Personally, I think that's quite confusing. You decided it was important enough to be constant and global, but not so important that you can't change the variable when you need to. So in this short program, again, we're including standard I/O for printing. we've set a global variable x to 4, and we've set a constant integer y to minus 6,000. And then in main, we're printing the value of x, where we have an integer pointer z pointing to the location of x, so it points to x. And then the pointer for z is set equal to x times y. Because this is a pointer to x, this is going to modify x. So if you then printf the value of x, you won't get 4, you'll get minus 24,000. I don't know why I made it so large. Another thing that you'll frequently see in the global scope in C programs are macros or other pre-processing steps. Macros are globally defined textual replacement rules which are applied to the code body by the compiler. So these are not parsed, they're not compiled in the traditional sense. It is a literal textual replacement rule which the compiler applies to the text of your program. They're extremely useful, for example, to write type-agnostic functions in C. This was kind of the way you did it back in the day. I don't recommend it. It can also be useful to define constants used throughout a program. For example, if you have a fixed size array that you need to constantly reference, this is a way to do so. They can also yield unexpected behavior in very weird and subtle ways. So here we have a program called bad macros. You can imagine it's not very good, where we define a macro that says square of a is a times a. Simple enough, right? In our main function, we specify float r1 and r2. We have float r equal to r1 plus r2. And then we're going to print the square of r1 plus r2 and the square of r. Now, from context clues, you might understand this is not going to give us the same value, because this is a very simple textual replacement rule. So it's going to take r1 plus r2 and write r1 plus r2 times r1 plus r2. So in fact, algebraically, it'll be r1 plus r1 times r2 plus r2. Only in very exceptional circumstances is that actually going to be the square of r. R times r, it'll give us 7. 7 is not a square, so that should immediately be a red flag. The correct answer is 16. The former is doing the textual replacement, so again, r1 plus r2 times r1 plus r2, which is 7, while the latter is actually doing things correctly. You can fix this macro. Instead of writing a times a, you could write parentheses, parentheses a, close parentheses, plus open parentheses a, close parentheses, close parentheses. Frankly, I think you should avoid the whole thing and just not use this macro. So we've been using data types quite a bit already. We've talked about integers, we've talked about floats and doubles. We've talked about size t even briefly, and pointers. Data types is a really important topic in C programming. We have primary data types. This is your integer, character, floating point values, void, which we haven't encountered yet. We have derived data types. That's like function, array, pointer, reference. And we have user-defined data types, structure, union, enum, and typedef. We'll go through most of these. Some of these are used much less often than others, especially in C. An important point to make here is that there are unavailable data types in C that you might be used to from other programming languages. So you might be familiar with the Boolean, which has true and false values, 0 and 1 typically. It's defined in a header, so if you do include standard bool, you can use the bool type. But if you don't include that, then there's no Boolean. This is kind of a headache for people coming to C from other more modern languages. This is a real throwback. The other important thing is that there's no string. In C, strings are character arrays. So a character type city array is equal to Durham. That's the closest thing you get to a string, unless you use the string header. And mostly you do that in C++ rather than C, because if you're using C, then you don't want to deal with strings at all. We can chat about some of the more informal elements of programming in C tomorrow. An important part of having this sort of rigidly defined type system is type promotion and conversion. It'd be really limiting if once you defined an integer, you could only interact with other integers. Especially if you have to write functions that then need to use, you have to write multiple copies to allow for different input types. You have implicit conversion between types in C. It's kind of sparing compared to, say, what you might be used to in Python. This is sometimes called type promotion. For assignment, type inference only applies toward a more general type. So if you start with an int, you can promote it to a float, but you can't automatically demote a float to an int. For computation, it promotes to the most general type, so either the inputs or the required output. And for comparisons, it's only valid between equivalent types. This is very important. There's some very, not necessarily subtle, but annoying bugs in C that arise because of this. If you are interested in like the performance of C and like rigorously typed systems, but you don't want to deal with any of the types themselves necessarily, Julia might be for you. You can come and talk to me about it. So let's look at an example of type promotion in C. We have an unsigned short int u set equal to 1. So this is, of course, an integer type, but it's a short integer, and it's unsigned, so there's no sign bit. So its range is from 0 to a large value. Well, not particularly large because it's short. And then we have int I set equal to the value of u. And then we printf u and I. This int I equal to u is an implicit type conversion. The int is more general than an unsigned short int, so it'll promote u to I. Then we have float a, which we explicitly convert from I. You do this by putting the target type in parentheses ahead of the variable. And then we have double b set equal to I divided by float u plus 2. And that line somehow combines both explicit and implicit typing. And then finally, we print the values of a and b. If you compile and run this program, you start with u equals 1, of course. That's hopefully not surprising. I is equal to 1, because this is being implicitly promoted. A is set equal to 1.00000, because it's a floating point type. And b is set equal to almost a third. Right? Because this is 1 divided by 1 plus 2. Hopefully that's not too confusing. A word of warning here. Implicit type conversions are a source of many numerical errors in programs. It is considered bad practice to rely on them, especially extensively. The syntax for designating an explicit type conversion is to prefix the variable name with the desired type in parentheses. Like here, we've done float in parentheses ahead of I. That's an explicit type conversion for the variable a. It is much better to do these things explicitly. Writing in C is hard enough. You should make your life a little bit easier by not relying on implicit things. Okay. Here we have some more type conversions. We have unsigned int u equals 1, int I equals to minus 1, double A is equal to 10 divided by 3, and then if I is less than u, printf 3a equals whatever. So u is not converted, u is assigned, I is assigned, a is assigned, and then we compare I and u, and if I is less than u, then we printf. So what is the output of this program? Somebody write it in the chat. Output is 10.0, something 10-ish, 9.9999. Okay. Nothing. This program does not output. Now you might look at this line and say, well, I is always less than u. I is minus 1 and u is 1. But these are different types. You can only compare between things of the same type. Now this is a subtle thing. I is minus 1. So if you think about converting this bitwise to an unsigned int u, this is going to be much, much larger than 1. It's basically wrapped back around, so it goes to the maximum value. So this program does not output. What can we do to correct it? Same variables. Okay, so one thing we could do to correct it is we could convert u to an integer rather than an unsigned int u. We might run into issues if u was actually quite large. In this case, it's small, so we're not too worried. We could try to down-convert I, but that's quite weird, right? I is negative, whereas if we made it an unsigned int, it could never be negative. So the easiest thing in this case is, of course, to just convert u, I less than int u. That'll make a correct comparison, at the very least. Another thing, we could replace a equals to 10 divided by 3 with 10.0 divided by 3.0, because with a we're relying on implicit conversions. What if unsigned int u is equal to minus 1 in this program? Say you've inherited this from some senior developer who's retired after 40 years. You've never seen this code before. This is a much thornier issue, right? Unsigned int u equal to minus 1, I'm pretty sure works if you compile and run it. But it will give you u equal to this large integer. You then have a thornier issue, which is what the programmer intent was. Now in this short program, we can probably infer intent because we've done some programming ourselves, we're paying attention. If you're new to the code and this was a much more significant code base or something, mission critical for your company or your project, this is a much thornier issue. It becomes quite philosophical very quickly. Should u be equal to this large number? Maybe. Depends what it's used for. Now this was because of underflow and overflow. You may have heard of this before. Computers don't know anything about numbers. They know things about bits. They really only care about two numbers, 0 and 1, and then we built everything on top of that. So this is a short intro to the binary representation of integers. You may be familiar with this if you've done a good amount of numerical programming before. We'll define some sequence of zeros and ones, followed by a subscript b to be a binary number. And for now, we'll just talk about integers, but we'll come to floats in a bit. Then a 1-byte sequence representing 0 is just 8 zeros followed by that subscript b. Easy enough. If we want to represent 55 and we want to increment that value, we can think about this in terms of binary format. So 1 is just 7 zeros followed by a 1 with a subscript b, and 55 is 1 plus 2 plus 4 plus 16 plus 32, which is 2 zeros, 2 ones, 1 0, 3 ones, followed by b. And the question is, how do we actually increment that 55 by 1? Of course, this is addition. We can define addition in terms of the binary representation. Easy enough. So we'll start by writing it out. We're incrementing that last digit. So we have a 1 and a 1. So this bold 1 here, it doesn't go to 2. Computers don't know about 2. It goes to 0. And this passes up to the next one. If you did manual arithmetic as a kid, I don't know if they still do that in schools, this will feel familiar. And of course that 1 continues to cascade because these were 3 1s, and it goes into the first place where there was a 0, and that then switches to 1. So now, instead of having 3 1s, we have 3 0s, and the next value up or down, depending how you look at it, goes to 1. This is how a computer does addition. It's looking at things bitwise. It has to do carryover. For addition, this is relatively straightforward. If I asked you to multiply, say, 1 and 55 in binary representation, where these are both 1-byte sequences, this would probably take you quite a long time, because you have to do every pairwise multiplication between each bit. So multiplication is quadratic in the bit length, while addition is linear in the bit length. In practice, they take about the same amount of time on modern hardware. So now the question is, what is the largest 1-byte number we can represent? Well, there are 8 1s. Sorry, it'll just be 8 1s here. So that's 1 plus 2 plus 4 plus 8 plus 16 plus 32. No, I missed somebody. 1, 2, 4, 8, 16, 32. Yeah. So all 1s in binary is just 255. What happens if we add 1 here? So 255 plus 1 is 0. In 1-byte modular arithmetic, this is sort of unexpected if you are coming from math rather than computer science, which reveals the modular nature of computer integers with finite precision. If you were able to allocate more bytes to representing these numbers, you could represent larger numbers. You'd have a larger range over which you got the expected result before overflow. Now, all these types have particular amounts of memory associated with them, and thus a certain range that they can represent. For a bool, it's sort of more complicated than I'm representing here, but bools can be 0 or 1. They are 1 byte. You'll note that 0 or 1 is 1 bit. So this is quite over allocated in that sense. A character is 0 to 255. That's 1 byte. A short int goes from minus 2 to the 15th to 2 to the 15th minus 1. That's 2 bytes. An int is 4 bytes and has a larger range. A long int is 8 bytes. It has a larger range. There's a float, which is 4 bytes and has a truly massive range. And then a double, which has a truly exceptional range and uses 8 bytes. We'll talk a bit about how float and double are represented in memory, because it's a bit different compared to integers. Yes, so all of these number representations have to make a trade-off in terms of memory usage and their precision or range, how reliable their results are in the middle versus toward the edges of their range. And floating point numbers make very different trade-offs compared to integers, as you might imagine. For floating point numbers, we have a binary integer representation where, of course, each bit is represented the same way. However, floating point values segment themselves into some number of bits for a sign, for an exponent, and for a significand, or what's sometimes called the fraction part. For a 32-bit float, so in C this would be a float, you of course have 1 bit for the sign. The sign can be positive or negative, so there's only 1 bit needed. It allocates 8 bits for the exponent, and then 23 bits for the fraction. So this binary representation gives you 0.15625. You can see that a lot of these are zeros. There's actually very few ones. This representation of floating point values also produces some rather unexpected representations. We'll go over a few of them. So these are floats. I think, yeah, floats. So 0 plus 0 in binary floating point is all zeros. Everything's a 0. You also have negative 0. That's where the sign bit is set. You can imagine this can be quite confusing, lead to subtle bugs if you're doing numerical work. You can represent infinity with floating point numbers, or at least we call it infinity. So this is just the exponent being all ones, whereas the sign is set to the positive value and the fraction is set to zeros. And you can have negative infinity as well by just flipping the sign. Now, in an earlier example, we had some value set to about 1/3. This is the floating point representation of a third. You'll note that it's not exactly a third. There's an error. It's relatively small, but it's not 0. So in your code, if you were using a floating point value and you knew it should evaluate to a third, and you wrote some line that said, if that value is equal to 1/3, it would always evaluate to false, because 1/3 is not representable in floating point numbers. This is in part because of the precision, in part because of the finite nature of things. You can't hit 1/3, but you can get pretty close. This is a problem that a lot of new programmers run into when they're doing numerical work, is they think they can compute things exactly, and they make some assumptions about what is representable and what is not, and then their code fails in spectacular ways because they haven't accounted for the way computers have to work. So this is a good thing to keep in mind. If you did want to check that some value is about 1/3, you take a difference and the absolute value and check that it's within some tolerance in practice. An important thing to keep in mind about floating point numbers is that their precision actually varies. So they're not uniformly accurate across their whole range. So here we go from 10 to the minus 20 to 10 to the 20. So that's 40 decades in floating point value. And on the y-axis, we have the precision of the floating point number. And F32 is a float, F64 is a double. So the distribution of floating point values on R is actually highly non-uniform. This can introduce really subtle bugs in your software. So for example, if you need to represent 10 to the minus 10, and you need an accuracy of 10 to the minus 30, even the double won't help you. You can even see that actually towards this high end, you get this, well, on the display that's 10 feet tall, it's really apparent that there's a staircase here. You may not be able to see that online. We typically talk about accuracy in terms of around 1. So around 1 we get about 7 for F32 and around 15 digits For F64, by 10 to the 10, floats can be inaccurate to about 1,000, while doubles maintain decimal accuracy, so accuracy of about 1, until 10 to the 15th, and then things get real weird. So you can do really dramatically different scales of calculations with floating point numbers, but you do have to think quite carefully about how well things are being represented numerically. Floating point bugs can be a really subtle and especially bad for scientific floating point bugs can be very subtle, and these are especially bad for scientific computations because we tend to make use of a lot of floats. So I mentioned that Boolean values are stored as 1 byte or 8 bits, even though they can only represent 1 bit of variation. In principle, a Boolean need only contain 1 bit of information, that's 0 or 1. The reason why is because there are limits to the addressability of memory. So your computer has a word size. It is almost certainly 64 bits. It can't address anything smaller than 1 byte. So every data type must be addressable, because if it's not, then what are you going to use it for? It must have a unique memory address. Your hardware addresses memory at the resolution of bytes. Therefore, a Boolean variable must be no smaller than 1 byte. There are exceptions to this if you are a very good programmer. There's something called bit packing. And this is an advanced technique where, for example, you store a single byte variable, but you can address individual bits by bit shifting. So for example, if you knew you only had to use 8 Booleans in your program, you could store all of them as a single bool and just read off individual bits by multiplying and shifting. I bring this up really to make the point that in software, we tend to make a mistake by thinking our programmatic constructions are hardware independent, that the code we've written here is going to be the same as when it's evaluated over there, and this is not always true. This is actually perhaps most acute for those of you who are coming into programming recently. So for example, that laptop is x86, this desktop is x86, my laptop upstairs is ARM. These are different architectures, and if I compiled even a very simple C code for x86, it wouldn't run on ARM. I could recompile it for ARM, and hopefully it would do the same thing, but guaranteeing that is actually a hard problem. So keep in mind that the software you produce has to run on actual hardware, and that actual hardware has certain constraints on how it works. So we've seen a size type once so far. If you haven't used C before, you probably haven't seen it before. You can think of size type as an unsigned integer type, which is really just meant for storing the length of arrays. Size type. You'll usually see it in code as size TL is equal to size of some array. That's really what it's intended to be used for. There are some pitfalls. So here we have a size type L1 equal to 5, size type L2 set equal to 6, and then size type A equal to L1 minus L2. And then we print the value of A. What is the output of this program? Maybe I'll ask a more specific question. Is this program going to output -1? No, it will not, because it's unsigned. It'll give us something rather unexpected. If you have a very good memory for numbers, you'll remember this number from earlier, it will give us the overflow value. So it won't give us -1. So in this program, we declare the length size to L1 and then L2. We compute the difference, and then we print the value of A. The unsigned integers are not closed under subtraction or addition. So if we do int A equals to L1 minus L2, that would give us expected results, especially if we didn't rely on implicit conversion here. This is an annoyingly frequent bug. because you do frequently want to figure out what the difference between two sizes is. And you're not always careful about ordering things, or sometimes people give you unusual inputs, or you've just lost track of things and you're trying to figure it out in the program. I've made this mistake. I know lots of people who have made this mistake. Something to keep in mind. Now that we are coming up on arrays, we do have to talk about pointers. And pointers is the thing where people typically bounce off of C. Especially if you come from Python, it's very different. So with pointers, the mapping from variables to memory addresses can be made explicit by looking at pointers. So of course, memory is enumerated using integers called addresses. Pointers are variables that hold the address. This implies that pointers are integer variables whose values are memory addresses. It is that simple. In practice, it's kind of hard to reason about. If we return to our declaration example where we have int x equals 4, then we declare y, and then we have an integer pointer z set to the location of x. The pointer z is a reference to the address of another variable, x. Pointers do several things in typical C programs. A basic pointer will store a memory address, of course. It might hold a variable, stores a memory address which holds a variable whose type imbues the pointer with a matching type, and by dereferencing the pointer, you can engage with the value of that variable. That's really all they do. In practice, it can be really difficult to follow. The reference operator is denoted by the ampersand, and when applied to a variable, say double x equal to 1, it gives the memory address of that variable. So if we, the dereference operator is denoted by star, and when applied to a pointer variable, it will return the value at the address stored in that pointer. If you think that using the star for both multiplication and dereferencing is confusing, I agree. The precise meaning of that star depends on the context in which it appears. This is really frustrating if you're trying to quickly read C code. When used in a declaration, for example, integer star pointer is equal to reference of x, then it creates a pointer variable. When used in other contexts, for example, int y equals star pointer, then it dereferences, giving the value. When used as a binary operator, int z equals to x times y, then it's the multiplication operator. C has been around too long for us to change this terrible design decision. We all just have to cope with it. Now, of course, the reference and dereference operators are usually used in tandem to manipulate program memory or do performance-critical work without the overhead of variable abstractions. So, for example, we have double x equal to 2, double pointer y, which references x, pointer z, float pointer z is a float pointer of y, and then you printf the dereference of z. One mistake early C programmers make is reusing pointers with incompatible types. This will lead to bounds violations or undefined behaviors. On the left the program on the left, we create a double pointer to x and then try to cast it to a float pointer. Of course, this is not allowed. Printing out the value of z at the end will show you that the casting is incorrect. Pointers in particular represent a number of hazards for code safety, including dereferencing a null pointer or inappropriate typecasting or having a pointer which is not designated to a specific variable. This is called a dangling pointer. Pointers are unfortunately still kind of required to write C code. Almost all modern languages are moving away from this type of thing. Even C++ really discourages the use of raw pointers, which is what these are. Instead, using what's called a reference or a safe pointer. In Julia, there's a ref value, there's a view as well. In Rust, there are pointers and references but they don't work in the same way. They have some nice properties where you can prove correctness for their usage at compile time. The C compilers do not prove correctness of any of this. When you're writing C code, you're kind of on your own. The compiler is at most an antagonistic friend. It's not there to help you. So pointers are simple in principle, really complicated in practice. There's a lot of really difficult bugs that they can produce, and you have to pay careful attention to how they're used. The most common use case is for arrays. Computers are very good at doing simple operations to a sequence of numbers. This specialty makes arrays the bread and butter of especially scientific computing. Formally, we'll think about arrays as continuous regions of memory which hold a sequence of uniform values. So you can have an array of doubles, you can have an array of ints. You cannot have an array of ints and doubles. So in this simple program, we declare and assign an integer array called int r with the square brackets. And on the right-hand side, we have curly braces which set 0, 1, 2, 7, 5. In this case, we have a fixed uniform, we always have a fixed uniform type. In this case, we have a immutable length for our array. This array is going to be allocated on the stack. That's what this syntax means. And in the next line, we take the value at index 3 and set it equal to 3. And in the last line, we have a pointer to the array plus 4, and we set that equal to 4. So your pointer to the array is always to the 0th value, the first value, the 0 index. If you add 4 to that, you go 4, and you change that to 4. So you can access values using the square braces and an index. You can do direct memory access through pointers and offsets. Simple enough. You can do multi-dimensional arrays in C. They're kind of infrequently used for various reasons. But, especially for scientific computing, it's really convenient to think about things in terms of multi-dimensional arrays. For example, a matrix or a higher order tensor, though in practice many libraries use single-dimensional arrays for these, it is helpful to think about them as two-dimensional arrays. So in this program, we have an integer array. We don't give a length in the first index, we give one in the second, and we just give a list of values. On the right, there's 6 values, and we say the last index is of length 3, so that first index has to be length 2. Then we have array 0, 2 set equal to 2, array 1, 0 set equal to 3, and then array 1 plus 1 set equal to 4, and array plus 1 plus 2 set equal to 5. Accessing things by index you are hopefully familiar with. That is pretty legible. This can very quickly become illegible. And in fact, this is not the worst case for manipulating the pointer. I think I'll give another example where it's even less clear. You can, of course, access or change the elements just as any other array, but accessing a multi-dimensional array using pointers requires redirecting. So the higher the dimension of the array, the more redirection. This can be rather expensive if you're trying to do something with high-performance computing, because you now have to skip through memory in an unusual way. Now, of course, for multi-dimensional arrays, there's substantially more freedom in the syntax for allocating these. This just reflects the fact that for n numbers, the ways we can arrange those n numbers grows quite quickly. With the number of dimensions, for example, there are 9 ways to arrange a 12-element multi-dimensional array without reordering the elements. This is like a cute little combinatorial problem if you are interested in that kind of thing. My controversial yet brave opinion is that most bugs in scientific software are indexation errors. We've tried to access memory directly and have an off by 1, or we don't quite understand how the indexing works in C, because it's 0-based indexing and we're used to 1-based indexing perhaps. This controversial yet brave opinion implies that when you have really complicated objects stored in memory, like multidimensional arrays, you do have to be quite careful about how you manipulate them. So when allocating a multidimensional array, I think it is good practice to specify the shape entirely. So in that example we just went through, the first index was left implicit, but I think you should be explicit on all of the indices, because it gives you, the programmer, a lexical way to check that you are iterating correctly. We've talked about types, we've talked about how they're represented in memory, we've talked about how you manipulate variables, and how you think about them in terms of their memory locations. We've talked about stack allocated arrays, what you can do with those, multidimensional ones. We've talked about pointers, at least briefly. I've given you a sense for some of the dangers and benefits of using them. Now we can move on to dynamic memory and the heap. Often you're writing a program and you don't quite know how much data you're going to be processing with it. For example, if you have stuff stored in a file on disk, you don't know how much is in there until you read the file in. Sometimes you just make an allocation and then find out it was too small. Or you have a really large allocation and you want to reuse it to do more computation without remapping it to a new variable, like if you're using a scratch space in memory. To this end, standard lib has us covered with 4 important functions. We can create a memory allocation on the heap using malloc or malloc. I think real C programmers say malloc. Lazy people like me say malloc. We can create an initialized continuous memory allocation using calloc. We can change the size of these allocations after the fact with realloc. But we must free the allocations we made on the heap with free. If you recall from earlier, stack allocations are handled by the compiler and the operating system. Heap allocations are not. They are the programmer's responsibility. If you use it, you have to unuse it. Now, allocating memory is done in units of bytes. So to allocate for an array which holds n ints, we need to call malloc with n times the size of int. So it's the size of an integer type in bytes multiplied by n. This returns a void pointer. That is, malloc does not assume a type for the memory storage, which is typically then cast to the pointer of the correct element type. Let's look at this in action. In this short program, we have int n equals 10, and then we have an integer pointer, which is cast to an integer pointer from malloc n times size of int. So malloc is just asking, how many bytes do you need? I'll give you those bytes, and then we have to tell the program what's going to be stored in those bytes. Then we can work with our pointer with the correct type. And then we'll have a for loop here, int j equals 0, j less than n, plus plus j, pointer j is j plus 1. So even though you've had to go through the pointer direct memory access route for the allocation, you can still manipulate things by index. I encourage you to do so. Doing it by direct memory access is a little confusing sometimes. If you know the type and the number of elements ahead of time, it can be more clear when you're reading your code to instead call calloc or calloc with n and size of type, then malloc n times size of type. Additionally, while malloc slowly marks the memory range for the pointer, calloc initializes it, preventing you from accidentally reading garbage data. So in that previous program, if we immediately started reading values out of pointer before we go to this for loop and actually put things in there, we'd just be reading garbage data, whatever that memory happened to hold when we got it. Yes, so in this case, same sort of deal, but now we have floats, and calloc is going to give us n size of float, I don't think you need to explicitly cast it here, but, have it. And then here, we're just assigning the values. So you use CALOC in a very similar way. It's interpreted slightly differently. Getting familiar with the use of CALOC versus malloc is something that comes with experience. Now, why would you use realloc? Well, sometimes you allocate for an array and it's too small. This is a common pattern in MATLAB, for example. So in this case, you have a MATLAB array y, and you're just saying y is equal to y 1 through n minus 1, or y through n plus 1. And in Python, you might do y.append x for a list. This is pretty common, especially in modern languages. In C, it's a little bit more onerous in the sense that, okay, we have our previous program where we're CALLOCing some memory for floats, and we're putting stuff in there, and then we are reallocating the pointer. So pointer is equal to a reallocation of the pointer 2 times n times size of float, which is of course larger than n times size of float. And then we have another loop into j equal to n, j less than 2n, j plus plus, where we use the direct access method here, and we just assign the values of j minus n plus 1.0. So up to this point, we had our old program, just 0 through n, not including n. In the second part, we go to 0 through 2n, not including 2n, and we've assigned everything in there. Now, of course, you wouldn't write a program like this to use realloc. This is for demonstration purposes. In a real program where you did want to reuse your scratch space, for example, it'll be a bit more complicated than this. You probably wouldn't want to only initialize the values in the new range, because then something bad might happen if you're reading the old value locations. Now, the importance of freeing allocations. You see malloc and calloc and realloc. These have all been bad practice, all the examples I've shown, because I haven't been freeing anything. Now, in the very simple examples I've had, it's acceptable because the compiler can actually prove that the arrays do nothing and don't matter. So if you actually compile and run these with a high enough level of optimization, there won't be any array at all. Generally, if you're using malloc or calloc or realloc, and you don't have a free to correspond to it, that is a bug, and potentially a quite disastrous one. In simple cases, like the examples that I've shown, we're really relying on the program exiting gracefully and the OS recovering the memory. So we're relying on like a higher level abstraction, the outermost container of our software system, to manage this. This is an added layer of complexity. It means that your program is incomplete. It also means that your program has to account for all the ways in which it might be called, suspended, or terminated. On a modern computer, it's not just running your C program. It's running a million other things. You've got Teams and maybe Discord. You're running a web browser, which is doing all manner of horrors. You should make sure that your code, your C code, your little C program, is as correct as you can feasibly make it. If you're using malloc or calloc or realloc, that means freeing the memory that you are allocating. There's a concept, I don't know if it's really discussed anymore when you're learning to program, called sympathy for the machine. I think this stems from when computers were people who were doing things by hand. The idea is that at some point in the distant past, a computation was done by a person, and if you wrote a really bad computation, somebody actually had to sit down and do it. Maybe the modern example is if you write a really bad app, your phone's going to get hot, and you might purge memory of the web browser you had open or something. The punchline is just call free pointer once you're done with that memory. It can be the last thing in your program, it can be in the middle of your program. Where it is kind of depends on what you're doing. But make sure that you are freeing the memory that you allocate, otherwise your program is not complete. Okay, let's talk about strings. Like I said, C doesn't have a built-in string type, but C has characters, and C has arrays, so we can make strings which are just character arrays. And these can be declared as mutable or immutable with a slightly differing syntax. So, this first one, a character pointer HW1 is hello world. This one's immutable. For the second one, we have a known length, so we provide that. Same thing. For the third one, we have an array of characters, very explicitly. This makes things, I think, quite clear. Note this /0 in the last position. That's the manual termination for a character, for a string. If we're interested in accessing the element at position 7, then we have, of course, our thing where we explain what we're actually printing, and then we just print things. For printing, this one I think is clear and concise. For this one is a bit less clear. This is direct memory access, right? So we have a dereference pointer to HW2 plus n to get to the end position. And on this one, we have a horror. Here we have n accessed at HW3. This works. You can think about it as this, taking the associativity of addition quite seriously here. Don't do this. I've seen it in code. It's bad. It is completely illegible. If I saw this in something you submitted from Escada, I would immediately look up in your program and see that n is not an array, and I'd say, what is this? Because I forget that this is a possibility because it's so awful. So don't do that. But technically you can. So character arrays, they're fine. I don't think you should be doing any string processing in C. It's the wrong language to do it in. We can talk about that tomorrow. You might be tempted to do something more complicated in C than just integers and floats, though. And typically you'll turn to structs or structures, which are user-defined conglomerate types designated by the keyword struct. If you come from Python, you might be familiar with classes. A similar sort of idea. This is a bit simpler, I think, than Python classes. So of course, conglomerate types are extremely useful. They're at least as useful as any of the basic types. Here we're going to define a struct called a student, and this will consist of an integer student ID, a character name of length no more than 256, and some floating point GPA. This is perhaps less relatable in the UK context, but there's also no concise form of the equivalent of GPA. And in our main program, we just have a struct student. So student here is a variable of type student, which is a struct. And the student is is declared but not initialized, so none of the fields have any values on that first line. We then have to assign them, so student.studentID is 1, 2, 3, 4, 5. We can use string the header in order to access string copy. So we copy Jerry Smith into student.name. We assign student.gpa to a floating point value of 0.0 divided by 0.0. This is also bad, don't do this. And then we just print information about the student. So this will just print the student ID, the student name, the student GPA. Structures are, of course, enormously useful. They introduce some performance and ergonomic issues of their own. You might have heard of array of structs versus struct of arrays. This is a consideration in high-performance computing type things. So for example, if you were doing like galactic simulations, you might have a particle type, a struct, which has like a position and a velocity and a mass and maybe a charge. And then you would just define your simulation in terms of particle-particle interactions. And then you'd have a long array which lists all of your particles. You can do that. It's not particularly performant because the layout of these fields in memory is sequential. So you can have very unusual offsets between important features that you are repeatedly accessing. The alternative is to define a type called particles, where each field is like an array of the various property of each particle. So structs are great. You are probably not going to use them very much in C, but they're good to know about. Okay, so that is memory and types, variables. That's not everything about memory. There's a very good article series detailing the physics of memory reading and writing, all the way up to practical advice for programmers by Ulrich Dreppe, and it's published on LWN, Linux World News, I think. So there's part 1, which has no subtitle, and then part 2, CPU caches, part 3, virtual memory, part 4, NUMA support, part 5, what programmers can do. This is an excellent article series. It's deeply technical, especially the first one, which I think is really about the physics of memory, or, the physics of memory when it was published. CPU caches are really important for doing things performantly nowadays. Virtual memory is really important for actually understanding what the computer is doing, because, like I said earlier, your C program is not running in isolation on the hardware. It's running under so many levels of abstraction, it might as well be magic. Part 4, NUMA support, that's non-uniform memory access. And then part 5, what programmers can do. If you're really just interested in learning a bit about how programmers should think about memory for doing things correctly and performantly, you can just read part 5, but I think they're all very good reads. So with that, I will end today's session.